Hello, my name is Dan Ghica and I'm going to teach you about game semantics. First of all, I want to say that game semantics is a denotational semantics. I'm pretty sure you have seen a lot of operational semantics in this summer school. And I'm going to try to explain very briefly what denotational semantics is by comparing it with operational semantics. And I'm going to give you a oversimplified picture because I don't want to dwell too much on it. And I'm going to skip over some technicalities for pedagogical reasons. So if you go and you pick up one of the very many excellent introductions to denotational semantics, you are going to see that some of the things that I'm saying now are approximate for pedagogical reasons. Sometimes you need to lie a little bit to tell a good story. But the idea is not going to be distorted. I think the idea which I'm going, the bigger picture that I'm going to paint, I hope is going to be an accurate one and one that is quite easy to understand. So first of all, a few words about denotational semantics. By contrast, with operational semantics. So what do we know about operational semantics is that it's a way to mathematically specify a programming language using rules of roughly this shape, where this is a term in your programming language, and there's also some additional configuration information. And you can express the behavior of a program by showing how a term t is transformed to some other term t prime, and also the accompanying configuration can change as well. And you can think of it as a symbolic step of computation. And it's a very nice way of specifying programming languages because, first of all, it is syntactic and it is self-contained. You can specify a programming language in terms of itself. It's very flexible, as we know, and in some sense is mathematically elementary, and that makes it very accessible. And together, all these things make it very useful to specify programming language and to some extent to reason about programming languages. By contrast, denotational semantics is translational. So you need a meta language which I'm going to call it the semantic domain. And usually the translation or the interpretation function is given by these fat brackets that are going to take terms in your programming language and take them into elements of your semantic domain. And the assumption is that in order for this to make sense, that the semantic domain is a well-understood mathematical universe. Or at least, if it is also a language, if you want to think in more formal terms also of the semantic domain as a language, then in some sense is a better understood language. Whereas the programming language is just an arbitrary programming language that has an arbitrary collection of features. And what's specific about this function, the semantic function, is that it's defined inductively on the syntax. So if I have a term where k is some syntactic construct and then t0 to ti are the subterms, this is going to be interpreted as a function f, which takes as arguments the interpretations of the subterms. So very important is that this thing is compositional. Compositional in the sense that the meaning of the whole is specified as a function of the meaning of the parts. And that is very nice. So for example, to give you a very quick example, which is not necessarily from programming languages, but hopefully to ground the intuition in something that's very well known, think about regular languages. You can work with regular languages syntactically, and that would be something like an operational semantics using clean algebras, or semantically using finite state automata. Right? So one is a more syntactic, one is a more semantic way of ultimately representing the same thing. So here, the thing that we want to represent in this example is regular languages. Right. Denotational semantics, unlike an operational semantics, is a more ambitious and a more intellectually involved exercise. First of all, it's not self-contained. You need to make a choice of the semantic domain, and then you have to find ways to translate programming language features into the semantic domains. And these translations may be less obvious. But this kind of high upfront investment will actually give you some profit. There is a payoff. And the payoff is reasoning about equivalences. Not of programming languages, but rather in programming languages. Reasoning about equivalence in programming languages is quite tricky. So let's take like a first stab at it. Just look at a simple example. If I have a rule, and suppose that in this rule the auxiliary configuration C stays the same, so I'm not even going to specify it, but I have a rule that takes a term T into some other term T prime. We might want to say that in some sense T and T prime are equivalent, right? Because why wouldn't they be equivalent, right? They are basically the same thing. T prime is just whatever happens to T after it runs a bit. So it should evolve into something that's equivalent. So that's reasonable enough, and we can take this for granted. But do we have any reason to believe that these equivalence would also be a congruence, in the sense that for all contexts, so a context is just a bigger program that has a hole in it. If we plug C, if we plug T in context C versus if we apply T prime in context C, do we still get two things that are equivalent? Well, we don't have actually a good reason to believe that in general. That doesn't have to be the case. It can fail to be the case for various reasons. One big reason is the presence of effects that is going to follow in the next lecture. Effects are going to follow, where things that might seem, let's say, mathematically equivalent, like x plus y is the same thing as y plus x, they are not equivalences in programming languages, because the phrases x and y might have effects. And if they have effects, then the order in which the effects happen is important. Another one, which is rarer, but nevertheless from the point of view of language design is just as important, is that your language could have crazy features present in the context. Like, for example, in many languages, you can have the ability of doing more or less, with more or less expressiveness, but to do things like reflection, which allow you to inspect a term. Well, if your term changes significantly syntactically through execution, and the reflection can allow you to inspect those syntactic differences, then that means, again, that equivalence is not going to be a congruence. And why is it important that an equivalence is a congruence? Is that these kind of equivalents are the basis for compiler optimizations. And compiler optimization always apply at the level of subterms. You don't want to say this big program is equivalent to this big program. You want to say this subterm is equivalent to this subterm in all contexts. So that's not something that we can just assume. In many languages, we can prove that certain equivalences are also congruences. On the other hand, so this is in operational semantics. On the other hand, in denotational semantics, usually, if you want to interpret a term in a context, that is going to be, if your denotational semantic is reasonable enough, because it's compositional, it's going to be an interpretation of the term composed with an interpretation of the context, where composition here is whatever notion of composition you have in your semantic domain. If your semantic domain is sets and function, then that is function composition. Which then means that your equivalence simply can be treated as equality in the semantic domain. Right? Because now this is just going to be equal to this, and this is just going to be equal to that. So it's, in some sense, this is no longer a problem, because we are going from equivalence in the programming language domain to equality in the semantic domain. And equality is always a congruence.
So the left side is the equivalence of objects in the semantic domain, or it should be equivalence of syntactic terms?
Sorry?
I think on the left-hand side.
The left-hand side of here? It is equality.
Yeah, it's equality
of object in the semantic domain. Yeah.
Okay.
And equality is always a congruence. So you don't have to worry whether it is a congruence or not. Okay? And because some of these properties are meaningful at a fairly high level of abstraction, then sometimes it is quite convenient, instead of working with concrete models that can be quite detailed and they could also be quite fragile, it is quite convenient to work for recipes, to work with recipes for models. And these are something that you can formulate more abstractly using category theory. I'm not sure, did you do any category theory this? No. Anyway, I'm not gonna spend a lot of time talking about category theory, but if you ever run into category theory, which is unavoidable, you can always think of it as recipes for models rather than models. Okay. Now, denotational semantics, one thing that it's less obvious than operational semantics. So it is less obvious that if you give a translational interpretation of a term, yeah, right. So it is just what I said now, is the fact that if you have a denotational semantics, then your equivalence in the programming language becomes equality in the semantic domain. And then you can reason about the equivalences much more easily. Reasoning about the equivalence using this definition, which has this quantifier over all the context, is very awkward. Whereas in the denotational semantics, every term boils down to a mathematical interpretation to an object which can be then compared for equality. And that equality, because also your semantics is compositional, is also congruent. Thank you. Right. So because the denotational semantics is far less obvious, it is pretty much universal that when a programming language is given, you always have the operational semantics. You take the operational semantics as a given because it's more likely to capture the intended behavior of. So, therefore, it's quite important to relate the operational semantics and the denotational semantics. Usually the flow is that you get an operational semantics first, and then you do the denotational semantics, and then you want to say, well, are these two about the same thing? So the first thing that's quite important here is that in relating operational semantics and denotational semantics, then usually it is to take kind of the most essential observational difference between program, we look at termination properties. So if a program T, and by program we mean something like a closed term of unit type, if it terminates, so if it evaluates to a constant, then we say, we put the down arrow means terminates, otherwise we say that it does not terminate. And in this case, the meaning of this program is going to get the meaning of this program that terminates is going to get a special element in the semantic domain, which I'm going to write as top. If it doesn't terminate, is going to get an element called bottom. Because that keeps things simple. At the level of the unit type, from the point of view of the observational behavior, you have only two observable behavior. A program that's closed either terminates or it doesn't terminate. Yeah?
So here that equality is kind of similar to what was the triple equality in the operational semantics over there, which, if I'm not wrong, you mean like a dynamics, right? So like if T steps to T prime, then T is congruent.
Well, this was an example, not a definition.
Okay.
The definition is I was actually going to literally give it right now. Because this was kind of informal. Now I want to make things a bit more formal. Observational equivalence, what does it mean? So that's exactly what I'm going to define now a bit more formally. It's still not completely formal because we're not in a specified language yet. It's just kind of, I'm talking a bit vaguely. But we're going to say that two terms are observational equivalent if and only if, for all contexts, and these are program contexts of unit type, term 0 in C terminates if and only if term 1 in term C terminates. So no matter what my choice of a context is, I won't be able to distinguish. Either both terminate or both do not terminate. And now, the key properties that relate these two semantics. The first one so the first key property is soundness, which says that whenever whenever two terms have the same meaning, it means that they are operationally equivalent. And that is kind of a bare minimum that you expect from a denotational semantics. If it identifies things which have different observational properties, like if you identify termination with non-termination, then it's pretty much nonsense. The second property, adequacy, is a deeper connection between syntax and semantics, which says that if you have a program that terminates in the denotational semantics, so it is assigned the meaning of the terminating program, well, then that's going to happen if and only if the program T terminates a lot harder to prove, you will find in the literature. It's a much more challenging result. And now going up on the level of difficulty, the third property, which is called definability, tells me that I have no garbage in the semantic domain. So for every meaning in my semantic domain, and there are some technical qualification here. I mean, this has to be in some sense a finite object in the semantic domain. There has to be a term in the programming language such that the meaning of the term is tau. Okay, so whatever, yeah.
I'm actually kind of confused. Shouldn't soundness mean that if two things are equal in the operational sense, then when you translate them, they're equal?
Having them, no, that's, let me just talk about this next now. Yes. So definability means my denotational semantics is translational. So to every term in the programming language, it assigns an element of a mathematical universe which we call the semantic domain. And basically definability says that in the semantic universe, I don't have garbage. I don't have meanings that do not correspond to terms. So everything I pick in the semantic domain, there is going to be a term such that its meaning is that thing.
What about completeness?
Yeah, yes, that's I'm going to say now. If all these three things hold, then we have a very nice situation, which is called full abstraction, which means something very similar to completeness, which basically says if two terms have the same denotation, if and only if they are observationally equivalent, and as a theorem, again, so this theorem is not really a mathematical theorem because I'm working in an oversimplified setting, but it's a recipe for a theorem that applies pretty much in all concrete languages with very small distinctions which I'm going to highlight. So the theorem says that those two propositions there, those two properties there, imply full abstraction. And let's look at the proof, because it's quite simple. One direction, of course, is just what I call their soundness. The other direction, let us assume, we're going to prove by contradiction. So let's just assume that we have T0 and T1, which have distinct meanings. And now we're going to derive a contradiction in the sense that they are not going to be observationally equivalent. So if this is the case, then there must exist, and the reason why this tau must exist is specific to the semantic domain in which you are. But it turns out that this witness, this semantic witness for the inequivalence always has to exist. There exists this witness in the semantic domain such that if I compose it with T0, it's going to give me the meaning of the terminating program, and which is obviously not the non-terminating program, which is what I'm going to get if I compose it with T1. So in some sense, I have a witness that can take non-equal meanings, test them, and reduce it to the comparison of top and bottom.
How do we know that interpretation of T1 composed tau is bottom?
Well, that's what I said. This is specific to the semantic domain because this is a recipe for a proof rather than an actual proof. So the conditions, the reason why that holds will depend on the actual interpretation that you choose.
Well, it's like a universal property. I mean, like every SD has a tau that behaves this way.
Yeah, except that it's not something that you can state as a theorem. But if it doesn't have that property, then it's a pretty poor semantic domain that you have chosen to work in. I'm not even sure if it would make sense, but yeah. Right? Now applying definability, which is the third property there, it follows that there is a C such that the meaning of C is tau. So T0 composed with tau, meaning of T0 composed with the meaning of C, which is the same thing as plugging T0 into C, which is equal to top. Therefore, by adequacy, which is the proposition 2, it follows that C of T0, because it's equal to top, terminates. Following exactly the same reason, we can establish that C of T1 doesn't terminate because it's equal to bottom. So in the same context, C of T0 terminates, C of T1 doesn't terminate, which is a contradiction. Okay? So again, this is a recipe for a proof, and this recipe applies just kind of anecdotal evidence from my own experience to all languages where you want to prove a full abstraction result. What you have to tweak is the actual meanings of these things here to make them mathematically precise in the context that you are using.
Isn't this just proof one direction of full abstraction?
Yeah, the other one is just the soundness.
Oh,
Yeah. Right. Okay, so this is all I wanted to say about denotational semantics in general. I mean, there are very many wonderful books about denotational semantics in general, which I urge you to read. In my notes, I give some references. But now let's move on to the main topic, which is game semantics. Game semantics is a denotational semantics, and the development of game semantics came out of an open problem, a long-standing open problem, which was the problem of definability for a programming language called PCF. Have you looked at PCF at all in this? Okay. So the question is, can we come up with a denotational semantics for PCF that has the definability property? And this turned out to be a very difficult problem. It was surprisingly difficult because PCF is a very basic functional language, and people thought, well, the denotational semantics of PCF should be something like sets and functions lifted in a certain way to take into account non-termination and recursion, so domains and continuous functions. But it turns out that it wasn't, that there was an operation in the semantic domain called parallel OR, which had no counterpart in the operational semantics. So there were meanings in the denotational semantic that corresponded to an operator that starts, a Boolean operator, or that starts evaluating its arguments in parallel. And if one of them, whichever one of them turns out to be true, it kind of cancels the other thread of computation, kills it, and returns true. So it's something in between eager and lazy. I mean, lazy would look at the first argument, then at the second argument, and that would be fine. But here you look at both of them, and when one of them returns true, you just say, well, I can kill the other one. I don't need to know what it is. And this is not definable in PCF. And then there was this was an open problem for, I don't know, 20 years or something like that. And game semantics came out of this effort as the denotational semantics that solved this problem. And it solved it by doing a quite significant, for lack of a less pompous word, let's call it paradigm shift in what a denotational semantic means. Because when people did a denotational semantics, they thought a function in the programming language is like some kind of function in a mathematical sense. And the game semantics took a very different view of functions, not as mathematical functions, but as processes. And then interpreted them using what really is combinatorial structures, way of represented sequences of interactions between a term and its context. So it's a semantics that happens at the interface, looking basically at the pattern of call and return, the pattern of calls and returns that can happen between a term and its context. It's been very successful. It led to full abstraction results for a whole bunch of programming languages, starting with PCF, but then many, many more. And in terms of full abstraction, is pretty much the only game in town. It's the only way of doing denotational semantics that led to this full abstraction results. Right. Now, before I begin, a warning is that the game in game semantics is unrelated to the games that you see in game theory. So there is game theory in economics, but these are kind of payoff games in which you try to maximize some kind of quantity, whereas these are combinatorial games. So if you want to think, like if you really want to think about the game, it's a bit like chess or NIM, games where whoever makes the final move wins. So the winning condition is being able to make the final move. Right? When you're out of illegal moves, then you lost. So that's how you can think of game semantics. And the origins of the game semantic metaphor and terminology are quite deep, going into proof theory, linear logic, and somehow they made it into programming languages via the Curry-Howard correspondence. But you don't need to really think of it as a game. You can just think of it as an interaction. So I would say just kind of abstract the game-like words that I'm using and just think of them just as interactions. The game or the dialogue or the interaction is carried out between two okay, so that's just, I said it's a denotational semantics. Interaction based. Two protagonists, P and O. P stands for proponent and O stands for opponent. But because nothing is actually being proposed or opposed, these are just historical artifacts. They could stand for, for anything, just to distinguish between the two protagonists. I will still call them proponent and opponent out of habit, but just think of them as meaningless labels. And these two protagonists interacts using moves. And there are two kinds of moves. So in total there are four polarities. So you have the OP polarities. You also have a question-answer polarity. As I said, what really happens in the game semantics, you trace the patterns of calls and returns which are possible between a term and its context. So the questions correspond to calls, function calls, and the answers to function returns. So we have four ways in which these moves can combine. Okay, so now let's look at some concrete examples. So let's start with something super trivial. The program that consists just of the constant 0. What can happen to this constant? Well, you can evaluate it. So that is the opponent, which is the context, is going to say, what is your value? And then the only thing that the constant can do is to answer, my value is 0. Yeah, that's the only interaction that can happen between that term and its context. Now, from now on, my examples have to be thought of as coming from call-by-name languages, such as PCF. And the reason, again, is didactic. The structure of the game semantics is quite deeply influenced by the evaluation mechanism. So whether it's call-by-name or call-by-value. And call-by-name games have a nicer structure. So what I'm going to do, I'm going to teach you about call-by-name games, and then having understood the basic ideas, it will be less daunting and much more accessible to read call-by-value games. But I'm not going to cover call-by-value games because there's no time. The ideas are the same, the manifestations are quite different. Right, another example, less trivial. The identity function on natural numbers. Yeah? Right, so, yes. Yeah, I'm going to, yeah. Let me not. So right now, I'm just going to give you some sample interactions. The interaction in which a term can interact with its context. In the case of a constant is unique. In the case here, it's also unique. It's only one way in which the interaction, in which the identity of natural numbers can interact with this context. So what's the first thing that can happen? The first thing that can happen is that the context can say, hey, function, what is your result? And the function is going to say, well, I cannot tell you what my result is unless you tell me what the argument is, right? So you have the dialogue. First, the opponent asks me a question, and then the proponent asks back a question, asking what's the value. Now, the context here can return any natural number whatsoever, because you don't know what this function is applied to. But eventually, it might return some natural number m, and here, so this is opponent, proponent, opponent, and then proponent, the term, what is he going to do? What's going to answer to the... Yeah, he's just going to copy it back to the environment. Such an interaction is called a play. The set of all possible play associated So you can think about the play as the possible calls and returns that can happen in one run for one particular context. The set of all plays is called a strategy, and this is our semantic domain. We are going to interpret terms as strategies, which is the set of all possible plays, the set of all possible interactions between the term and its ambient environment. Okay, so now we are going to start defining things. An arena is where the games happen. It tells you what the moves are and what the relationship between the moves are. So an arena is a tuple, M, Q, I, turnstile, where M is a set of moves. Q is the subset of questions, and conversely, A is the subset of answers. I forgot one thing in the tuple here. O is the subset of opponent moves. P is the subset of proponent moves. I is a distinguished subset of opponent questions, which are called the initial moves, right? In this example, this was an initial move. This was an initial move. These are, let's say, the designated moves that can start a computation, a play, an interaction. And finally, turnstile is an enabling relation, it's called. It's a relation between questions and moves in general. It is called the enabling, which gives you a basic causal structure in the moves. So for example, this one, every question enables its answer. Like you cannot have, in the call by name games, you cannot have an answer that doesn't correspond to a question. And also, you cannot have an argument being interrogated without the function having been interrogated. There's no way in which I can have a function, lambda x dot x, which is using its argument if I'm not trying to evaluate the function. Functions don't have this kind of autonomy. It makes sense for processes. Processes are very unstructured. You can have a process that, it automatically or for no reason asks for input. But a function is not, it has more structure. A function asks for input only if you ask the function to produce a result. That's the enabling relation. And the important thing here is that if M enables N, then M is an O move, if and only if N is a P move. This enabling, because these are, we're looking at the model that happens at the interface. So we always have this kind of, an output justifies an input and an input justifies an output.
What is A?
Sorry? A? M. A is the set of answers. So these are questions. These are answers. These are opponent moves. These are proponent moves. And the initial moves are the only ones that do not have to be enabled. That's how things get going with the initial moves. For example, let's look at the arena of natural numbers. The arena in which these games happen, which are very simple, so we have a set of moves, which is the natural number, sum, and some distinguished element. That element is the question. That set with a distinguished element, that is the set of questions. That is also the set of opponent moves. That is also the initial questions. And the enabling is between that and natural numbers. We also have a degenerate unit arena where all the components are empty, which is going to be seen to play a role. It's not it has its own role, this empty. Right, so arenas can be specified directly like I just did, and usually that's how the arenas for base types are specified. But we can create composite arenas, and because we're going to talk about programming languages, we're going to have a product arena and an arrow arena. Of course, you can have a lot more arenas corresponding to all sorts of other type structures, but for the point of teaching, that's going to be enough to take us somewhere interesting. A times B. So the product of two arenas is basically essentially taking the disjoint union of the two arenas across all the components. So it's the disjoint union, or rather the sum of the moves, the sum, the questions are the sum, the initials, are the sum, and the enabling relation is also the pointwise. So if you think about your arenas as some trees or DAGs or whatever, the product is simply situating the two arenas side by side. The arrow arena. The arrow arena, I'm going to draw you the diagram first, and then you're going to see why the formal definition is as is. So I have my A arena. I have my B arena. I put them side by side, just like here, but everything that is initial here is going to justify everything that is initial there. Because what it says is that whenever I start the computation in B, I can either carry on in B or I can move over to A. So I can either work in the body of the function or I can transfer control to the argument. So what does this mean? The moves are MA plus AB, MB, QA plus QB. I forget again, I can see it. Now here what's going to happen is that a proponent move is a bit like an output, an opponent move is a bit like an input. When I put an arena in the contravariant position, the opponent-proponent, the input-output polarities have to be reversed. So what used to be proponent or P moves in A become O moves, and O moves become P moves. All the initial players are going to be taken, or the initial move are going to be taken from B. And the enabling moves, the enabling relation is whatever I had in A, whatever I had in B, plus union, the right injection of B now enable everything in A. Okay? So let's see a quick, nice theorem. These two arenas are isomorphic. A times B arrow C is isomorphic as an arena with A arrow B arrow C. So that obviously corresponds to currying, and the proof is very easy. You just construct the two arenas, and you can see that in both cases you get this: A negated B negated C. All right? When you construct this and when you construct that, in both cases you get this structure. Why is it an isomorphism and not an equality? Can anybody spot quickly the reason? Is because this kind of coproducts of set is only associative up to isomorphism. So the inline and in left and in right operations mean associating some unique tags with the moves. Whereas here, First you do this, then that. Here you do this, then that. So you see they are associated differently. So the tags are going to work out differently in the composite arenas. So you just have the isomorphism is just going to change the tags between the two arenas. And also we have that this unit arena times A is isomorphic to A times I is isomorphic to A. So it is a unit for the product arena. Again, basically when you do this, the product involving I, then one of these is just going to be empty, but you are still tagging everything. So the isomorphism is just, so here you are removing all the tags, tagging on the left, tagging on the right.
What is I, U, R?
Sorry?
What is the I, U, and R before the parenthesis for I, B and
In right and in left. So if I have A into A plus B, B, in left, in right. So you can say something like in left of A is A0, in right of B equals B1. So I'm putting some tags on the moves of A and B, so then I can safely take the disjoint union of the two. Okay? Right, so because this business of the tagging, I showed it here quite kind of explicitly, but just so that we don't get lost into the bureaucracy of the tagging, I'm going to, whenever it's reasonable to do so without a lot of confusion, I'm going to assume that A and B are disjoint sets. So here we can take the disjoint union safely without having, without requiring these distinct tags. Okay? Right. So these are the arenas. These are where all the games are happening. Now let's look at place. And let's look at place in a slightly more complicated function. As an example first, before we give the definition. So you have a function that is going to evaluate its argument twice and compute the sum. So the interaction is going to start here. Then the function is going to say, what's the value of argument? It's going to give me some m. And then it's going to ask again, what's the value of the argument? And because this is a call by name language, and I'm not saying it's PCF, it's an arbitrary call by name language, it might have side effects. So the second time when you interrogate the argument, which is just a thunk, it might produce a different value. And then you return some p, which is equal to m plus n. So there is going to be, so we know that, we have an enabling relation here. We have an enabling relation here. We have these kind of enabling relationships that come from the structure of the nat arrow nat arena. What turns out to be important is that, see, when this move here happens, it is allowed to happen because it has been enabled. So an enabling move has occurred, but in fact here, two enabling moves have occurred. This one and this one. And it is important to keep track of which one is which, because we're dealing with patterns of calls and returns, and if we look at a sequence of call and returns, we need to know, it turns out, which returns correspond to which calls. So these correspondences have to be made explicit. So the representation of a play is going to be sequence plus pointers. So in this case, we have, okay, so now here I have to use these injections because we have nat, arrow, nat. So it's the same arena used twice. So definitely we cannot just say the disjoint sum. But I'm going to try to make these tags as lightweight as possible. So I'm just gonna indicate here that all the moves here are going to be tagged with this prime. So prime is just a syntactic tag applied to the move. So n prime means n with a prime tagged on. So here, if you want to write this sequence flat, it's going to be Q, question, M prime, question prime, N prime P with pointers attached. Now, because we are going to talk about the formal properties of these sequences, we have to represent this in a formal way. And the way we are going to represent it is as follows. Whenever I write a move, is going to be associated, basically I'm going to give the names of the pointers. So Q, A, B, followed by, so you see, this is the first move Q. It is enabled, this name here, it's useless because it doesn't link to anything, it's just residual, but it introduces the name B. And now this move, it uses the name B. So if you want to think of them as pointers in a language like this is where B is malloced, and this is where B is used. Okay? And then we have M. Oh, and it introduces its own name, C. M is connected to C. Q, this Q here, what pointers should this Q prime use? If you look at this diagram, which pointer should it use? What name? No, this is used, this is introduced. B. And then N prime uses D. And finally, the last one, P, uses B. Right, so these are required to keep track of what calls correspond to what returns, and also what argument calls correspond to what overall function calls. Yeah?
Sorry, I just don't understand why the opponent asks for the argument twice.
Because it's called by name. That's what I said. So in call by name languages, the arguments are passed around as thunks. So whenever an argument is used, it is actually re-evaluated.
Oh, so it has to evaluate it again.
Yeah, it has to evaluate it again. So it's
not asking the proponent for it, it's asking itself sort of to evaluate it.
no, it asks the context. So if you have something like lambda x plus x, And here you have something like some variable which gets incremented, right? So this x is going to ask it first time, what is the value of v? It's going to give the value and it's going to increment itself. And when it's used again, it's going to ask here again what's the value of v, and it's going to increment it again. So this happens in the context, this happens in the term. But all you see here is that at this point, this is proponent, so the P, it's a P move, so that means control is transferred outside. And then from the outside, you just get the value. And here, something is going to happen between here and here, but you don't see it because you only see things that happen at the interface. You don't see that happens in the two components. So we're going to look at how composition happens because this is very important. So that's going to be taken care of via composition. Okay. So now let's define what a play is. A play is a pointer sequence. These pointer sequences in the lingo of game semantics, sometimes they're called justified sequences. It's a pointer sequence in arena A such that it has two conditions. If P prime followed by some move with address A is a prefix of P, so this means prefix, then there must exist some question such that that question, and every move has some address, but in this case the address doesn't matter. What's important is that it introduces the name A. And it's going to be in this prefix. So in every prefix where a move has the address, uses the address A, that address is introduced by an earlier question such that that question enables the move in my arena. Right? And you can see that this happens here. This move, is it justified? Yes, by B, which was introduced here. Does Q enable Q prime in the arena? Yes, and so on. The condition is satisfied. The only exception is the first move. If Q, A, B is a prefix of P, so this is how it starts, then Q is an initial move in the arena. Yeah? This is the initial move. It doesn't, this name here is basically garbage. This one here. Now, this play structure that every move has to be explicitly justified, it really gives you the basic causal structure of the computation. It tells you when things can happen. I cannot have an argument that's evaluated without the function being evaluated. I cannot have a function returning a value if it hasn't been evaluated. And again, you can see how this is unlike processes in general. If I have a process with inputs and outputs, it can arbitrarily request inputs, it can arbitrarily produce outputs. But here we have a very elaborate causal structure described by the arena, and things can happen only if they are consistent with that causal structure. Yeah?
Just for a question. Do you have game semantics for process calculus?
Yes, there are game semantics of pi calculus, yeah. Yeah. I was going to show something like this if we have time, but at the very end. Because it's a bit different, the style, than what we're seeing here. Okay, so now we can explain, or we can define, what a strategy is. And that's what we can end with, I think. So the strategies are our semantic domains. This is what we're going to use to give meaning to terms. The strategy on an arena A, written sigma on A, is a set of plays such that, and now I'm going to give some closure conditions. For any P in sigma, if P prime is a prefix, then P prime is in sigma. So it's prefix closed, and that's okay. And by prefix, I mean at this level of granularity. So now when I'm talking about move occurrences in plays, I mean the moves together with the pointer information. We never break those apart. That's the level of granularity at which move occurrences happen. So if we take a prefix, then it's going to be in the strategy. And of course, if we want to say that the strategy records a history of all the interaction, history is prefix closed. You cannot change history unless you are a very, authoritative politician, I guess. But usually it doesn't work. You have to preserve history. The second one is if I have so P is a sequence, is a play that is in the strategy. M is an opponent action, and that opponent action can be used to legally extend my play. Then this legally extended play also has to be in sigma. So my strategy has to say, it has to take into account any legal behavior of the opponent. So the opponent cannot do arbitrary moves, but it can do legal moves. So, for example, it cannot make moves which are not justified in my sequence. But if it can make them, then they should be in the strategy. So in some sense, my strategy has to be a complete specifications of what happens. And finally, for every permutation pi on names, so these are so these names that I'm using here, A, B, they come from a set of names, which is an infinite set of names. So for every permutation action, if I apply the permutation action to P, I'm still in the strategy. So now what does it mean to apply a permutation action? Well, permutation action applied to the empty set is the empty set. Permutation action applied to some move with a name and a pointer is M, together with the permutation applied to A, and then the permutation applied to B, and the permutation P followed by permutation applied to P followed by, and the permutation applied to P followed by MA is right? So, do you understand what I wrote there? Is it obvious, or? So this is a bijection on names, and basically what I'm going through my entire sequence, and I'm applying that bijection to all the names. So I'm renaming everything to something else, and basically the fact that I'm closed over a permutation action, this is technically an equivariance condition. What it means is that the names play no special role in the strategies. So here when I wrote A and B, these A and B are never part of the behavior. It's a bit like, it's a generalization of the notion of alpha equivalence. So you can think of these strategies being defined up to alpha equivalence. So the choice of names is never relevant. The only thing that's important is that whenever I introduce a name with this notation, these names are always fresh. They're always new. Okay, so I'll stop here. And what we're going to do tomorrow, I'm going to give some examples of strategies, and then show how strategies compose, and then give a concrete game semantic model for a language that has high order function, has concurrency, has semaphores, and has local variables. And we're going to show that it's a fully abstract model. Okay, thank you.